can we welcome Christian to the stage?
I think I don't have any computer yet.
That's important.
Oh, it's just, okay, all right. I just right. Laser pointer, okay. Yeah. Great. I was a bit confused for a second.
No worries.
Can I start?
Yeah.
Great, so welcome, I'm Christian Lewe. I work for Blockstream Research, where I mainly work on simplicity and Miniscript. And it's great that we just had a talk on Miniscript, so you all know why Miniscript is great, why you should use Miniscript. And in my talk, I want to go beyond that. So let's do a very short introduction. Could you remove like the mouse or something? Like people in the back? Okay, great. That confused me. So we just saw that Bitcoin script is complicated. The previous presenter did a way better job at explaining that, doing this nice quiz. This was great. I just have one slide on it, which is a very common smart contract. It's used in Lightning. And even though it's ubiquitous and it's not so hard, like it's what the script does is not so complicated, it looks complicated. And there are many footguns. So it turns out that this is represented with this very short Miniscript. It's the same. Miniscript is Bitcoin script with structure. And particularly humans, but also machines, can reason about this way more easily. It has a tree structure. We can see an OR, an AND. We can see some public keys, some hash pre-images. This is much better for the eyes and much better for machines to reason about. I will just go very quickly about benefits of this. So benefits of structure. We can make sure that our scripts are correct. So the intended spending paths that we want are there, and unintended spending paths are not there. So hackers cannot spend our coins. The scripts are non-malleable, so no one can take my transaction and fiddle with the witness in a funky way to bump the fees or something. Scripts are composable, like we had in the previous talk, so I can take two scripts from different sources, combine them into a larger script. Those two sources don't need to talk to each other, and I can reason about the resulting script. I can try to find a witness for this resulting script, which is great for interoperability. I can analyze the script statically by just looking at the script, so I can see what are the fees, what fees do I expect, do I hit any consensus bounds that will prevent me from spending my coins. And all in all, the scripts are machine readable, so I can use my scripts in third-party tools to reason about them, but also in tools that Merkleize my scripts, that I can use them in zero-knowledge proofs and all these kinds of things, so that's great also for the future. So what am I talking about today? I'm talking about simplicity, which is a new blockchain language, and it has all these benefits that I just talked about. It is structured. What it brings to the table is it has arbitrary computation, and I will talk about what that means. And it's formally verifiable in a stronger sense than Miniscript. So that's exciting. Let's dig in. So what do I mean by arbitrary computation, which seems a bit opaque? One way to put it is I can compute every finitary function, which is a function from n bits to m bits. And maybe you have some idea what this might mean, but maybe this is still kind of very theoretical. Maybe you don't understand what this means. So another try. Every function that eventually holds. So with simplicity, I cannot write a Turing machine that will loop forever, cannot write any infinite loops. We don't want that, right? This will be an anti-feature. I want to have a finitary function. But still, what does that even mean? I don't know. Third try. Every function that you care about. And even though this doesn't really help in a way, it at least reveals a goal that we have of simplicity. We want to enable every function that you might want to have on the blockchain, which does not DDoS the blockchain, which does not have infinite loops. All of these things you can do with simplicity. You might not know what this means, but I will go into 3 concrete cases that are enabled with simplicity that we cannot do right now. So, well, first, the computation model. So because simplicity seems complicated. It's actually not. It's actually simple, as the name implies. So we have a witness when we spend the script, the program, we call it a program. There were some signatures and pre-images. We have the transaction, which contains the log time sequence and all the transaction data. And the simplicity program tells you, spent or not spent. That's what it does. There is no state, there is nothing of that sort going on. The programs always terminate, and there is no expensive introspection, so we do not need expensive index structures, anything of that sort. So they're actually fast to execute, even though they are so powerful. One concrete thing we can do is universal sig hashes, which are pretty cool. We wrote a blog post about it a while ago. So maybe you know the sig hash modes. When I have a signature in Bitcoin, I sign certain parts of the transaction, and I commit to these parts, we say. And this means if I change these parts, the signature becomes invalid because I committed to them. But on the other hand, if I change the other parts that I didn't sign, that's fine, the transaction is still valid. And this is really important for Lightning and other schemes. So the uncommitted parts are malleable, and in Bitcoin script, we have like 6 modes we can use. But 6 is that's not a lot. We can do much better, and we can do much more with simplicity. So one thing we can do, we can write basically a simplicity program that implements the hash. One thing we can do is we can have a conditional that says, I sign that the time lock is greater than a threshold. We cannot do that right now with Bitcoin script. I can sign a ratio, so I can say, I don't care about the amounts, say if we have an asset like on Liquid. I don't care about how many units of the asset I have and how much I spend for this. I only care about the ratio, which is the price. So I only want to buy this asset for this much, but you can malleate, you can change how much I buy, because I just want to buy for this price. I don't care how many units you give me. I can sign a covenant, so that's pretty cool. I can sign that the covenant is being upheld. This I sign. And many of these things rely on delegation aspects, so I can actually plug in the sig hash mode I want to use at signing time. And you can also restrict which parts you can plug in and which you don't allow to be plugged in. And what we can do is we can say, in the sig hash mode, I don't actually sign at all. I give my keys to another party. I can control which party that is, and then they can spend. So I can transform a sig hash for a signature for my key to a signature to someone else's key, which is pretty cool. And this is much, much more powerful than any old hash function, because we can compute the hash at spending time. Something else is ZKP, very popular these days. And the problem with ZKP is we need a soft fork usually. With simplicity, because we can compute any function, any finitary function which includes ZKP verifiers, we can build this in simplicity without a soft fork. We can try it out. And in the previous talk, we had confidential transactions for privacy, so they use something called bulletproofs to hide the amounts. And this uses the zero-knowledge property of bulletproofs and zero-knowledge proofs. And we can do roll-ups with simplicity, so we can implement a snark and use the succinctness property, which means that we can compress the computation, make the proof very short, logarithmically long, and make the verification time very short, also logarithmic, which is great for scaling. We can write all of this in simplicity and try it out. And in general, we can do also custom crypto. So if you want, you can implement pairing. You can implement a different curve and do BLS signatures. We can do SHA-3 if you want. You can implement that. We actually implemented SHA-2 in simplicity, so that's possible. We can do SHA-3. We can do identity-based encryption, which not many people know about these days, but it's pretty cool. And infinitely many more things. So it's all about trying out new things without needing a soft fork. These things might be expensive, but you can still try them out on your local machine, and if the community is excited, they can decide to speed this up, and I will talk about what this means. I want to talk a little bit about common misconceptions. So one thing you might think is Bitcoin script is already sufficiently expressive, because someone managed to convince me that Bitcoin script can do much more than people might think, using very impractical ways to use the script and using bit strings. So I'm pretty convinced you can compute everything that Simplicity can compute. But the problem is these constructions are, like I said, impractical. They're huge. Bitcoin script is not meant to have arbitrary computation, whereas Simplicity is. So Simplicity is much more elegant, much shorter. It's meant to have arbitrary computation. Bitcoin script, on the other hand, is not. So this is technically true, but actually it's not. I want to talk a little about the structure, because Simplicity is new, but it's still very similar to Miniscript, actually. So we have a tree structure, and they use the so-called combinators. And they're like puzzle pieces you put together in a tree kind of way, in a recursive kind of way. You can see that these combinators take a different number of arguments. So we have ones that take no arguments, these take one argument, and these take two arguments. You just plug them in like in Scratch, and this is your program. And all of these have a meaning that I will not talk about. And it's no coincidence that this looks very similar to the BDK playground, where I took this from, because, like I said, Miniscript is very similar. It has a tree structure like Simplicity. The only difference maybe is that here, these puzzle pieces have a more high-level meaning, whereas in Simplicity is more like an assembly-like language. So it's much more low-level. The puzzle pieces do very specific things, whereas these ones do high-level things. I want to show you very quickly some Simplicity programs, so you can go home and say you saw some Simplicity today. I will not go into like the details, because there's no time for that, but this is a keylog. So you can see you have a public key, you have some SIG hash, you have a signature, which is in witness data, and you have some Schnorr verification in some kind of tree structure. You can do a hash lock, so there is some hard-coded image that is your target. You have the witness data, which is a pre-image, some hashing, and some equality check. And you can do a time lock, so you have some threshold, you have the log time that is read from the transaction, and you check if for less equal. So Simplicity programs are tree-shaped. You can represent all functions that terminate all finitary functions, and we call this core simplicity. So core simplicity is all the programs that we can represent using the combinators. And we prove that this is complete, so we can actually represent all these functions that I claimed we can represent. But the obvious downside is some of these programs are large, especially things like a Schnorr verification. We wrote this in Simplicity, it's rather large. So we need some shortcuts, and we call them jets. So for some of these programs that compute useful things, we decide, I care about this, or the community decides, I care about this, I put this into a jet, I make it a jet, speed this up, I write some C code that speeds this up, I define a jet. And this is a subset, therefore, of core simplicity. And what this also means is that suddenly I have this design space for new opcode. So because Simplicity can compute everything we might want on Bitcoin eventually, we already know, in a way, all possible opcodes that we could ever invent. And what this means is, if we merge Simplicity, or if we think in terms of Simplicity, a new opcode is a new jet, and it's somewhere in this core bubble. We have a way of talking about a new opcode in a structured way, and we can also verify that the opcode does what it was intended to do, and I will talk about that shortly. Another misconception: Simplicity cannot be almighty because of consensus limits. Of course, so even though we can do all functions, we can compute all functions, actually some functions take a long time to compute, and we do not want to DDoS the blockchain, so there are consensus limits, but this is true for Bitcoin script too, and the solution I just outlined. So everything we care about that we want to be fast, we create a jet for it, which will speed things up. So this is not a problem. Formal verification. a scary word, I know. I want to talk a little bit about that. So this picture is maybe helpful. So on the left-hand side, we have the simplicity stack. On the right-hand side, we have this Miniscript stack. And we have a simplicity program, which has some formal semantics, so we actually know what this means in a mathematical sense. And this is executed on the simplicity runtime, which again has a formal representation, so we know what it is. And we have some jets which are written in C code, and we actually write this in verifiable C, which is a subset of C, and this also has mathematical semantics. And all of this is executed on the verified C compiler, which is proven to be correct, so we have some guarantees for the binary as well, which is important, right? We don't just prove mathematical theories on paper, they actually hold for the binary as well. This is much more solid than Miniscript, which itself has a formal semantics, and it's great, but we really had to fight to get this, whereas underneath it, it's much less formal. We have the Bitcoin script, which arguably is formal in a way. It has some C code. It's based on the C++ standard, which has a definition, but it was never meant for formal analysis. And it has some really funky semantics, which might surprise people. It's very hard to do. It's very hard to verify things with Bitcoin script. Let's talk about things we can do with simplicity now that we cannot do maybe with Miniscript, because we can prove more things with simplicity. I made some figures to illustrate this. So one of the applications is subroutines. So I talked about how we can write all these funky math gadgets like a SHA-3, a ZKP verify. Those are complicated programs. How do I actually know that they're correct? And this is even more problematic when these programs become really large, or I nest programs in programs. I need to keep an overview of things. So I need to know that the math gadgets produce the correct outputs. And what do? I write a formal specification, so this can be in hexspec or in another language. And this specification has some formal representation, which is this funky spiral, or whatever the shape is called. There's a mathematical object. And I have some simplicity program, so this could be the SHA-3 program, something I write. And because it's simplicity, we have a way of putting this into the mathematical realm, which is this other spiral. And what I can do is I can use a proof assistant and show that these are the same. And maybe they don't look the same, but when I look at first glance, but when I do the math, they turn out to be the same. And then I can be sure that the program implements a spec so that I verify the program, which is great, and we should do this much more when so much money is involved. Something else is opcodes. So, and this, Jonas Nick talked about this at TabConf about provably bug-free BIBs, which is really cool. So when you read BIBs, you often that specify a new opcode. You read something like, this opcode fails if any of these things are satisfied, or it does nothing otherwise. And this is an informal specification. And if you look at the Taproot BIBs, they have some pseudocode, maybe some Python code that helps. This is also an informal specification. We can do better than that. So we can write things formally, like in hexspec, and the bib for half aggregation is written in hexspec, I hear, which is cool. And what this means is the spec has, again, some mathematical formal structure that we can extract. So we can clearly communicate what we actually mean. There is no ambiguity in our words because math doesn't allow that, which is why we do this in the first place. And we can also execute some unit tests on the spec and verify it. And what this means is, in the case of simplicity, an opcode is a jet. It's some jet C code. And we write this in verifiable C, which again has we have a way to extract the mathematical object, so the function that this code computes. And again, we can prove that the jet implements the spec, or it implements the spec by proving that these representations are the same. The spec and the implementation have the same mathematical representation. And this will make our opcodes much more fault resistant, in theory bug-free, but this is obviously difficult. The spec has limits, but it's even just writing the spec, not even if we skip this step, writing this spec will be a huge improvement. So, and Simplicity enables that, and also enables us to verify the opcodes if we wish to verify them. And you can do much, much more than that, but I will limit myself to these examples. In a way, Bitcoin script is already verifiable. We can do manual audits. We can go line by line and check this code does what I wanted to do. We can keep track of the state of the contract, and we did this in a way in the Miniscript talk to find out why the scripts are wrong. But this is kind of tedious, and it was never really meant to be done this way. With Simplicity, we try to make it easier to verify, and we will also try to give you some building blocks, some ready programs that already have a lot of theorems, a lot of guarantees that go along with them, and you can combine them in this plug-and-play fashion to write larger programs that are correct, that you can prove relatively easily to be correct. So you have this verification toolkit. We try, Simplicity is meant to be verified, whereas Bitcoin script can be verified, but it's not explicitly designed to be verified. We go beyond Miniscript, so let's talk about how we can actually map Miniscript into Simplicity, because they're so similar that we can do this very easily. They're both a tree structure, and so what we can do is we can do a recursive conversion. We can convert the nodes, so a signature becomes a signature, a pre-image becomes a pre-image, and so on. And then recursively, we map all these children. So in the end, a Miniscript tree becomes a Simplicity tree using this recursive conversion. And we can always look at the Simplicity program and say, oh, this came from this Miniscript source. So it's not nearly as complicated as the Miniscript compiler. It's much, much more straightforward. It's by bijection, as far as I know. And we are working on a tool that lets you do that. So I think we call it the Miniscript Simplicity Bridge. So you give it a Miniscript hex, a Bitcoin script hex, and it gives you an equivalent Simplicity program. And we are also working on other tools that will help you visualize the program, the tree structure, and many other things. So that's exciting, and stay up to date for an upcoming blog post on that. And this was the semantic side. We can also talk about this was the syntactic side. And we can also have the semantic side. So we have a Miniscript script, and that's syntax, and it has some meaning. So this is the semantics. And we have a Simplicity program, and it also has some meaning. The meaning is the spending conditions that it implements. So when can you spend the coins, when can you not spend the coins? And I talked about how Miniscript is weaker than Simplicity, and how we can convert Miniscript to Simplicity. This is this arrow. Well, what we can also do is, the semantics of Miniscript is also weaker than the semantics of Simplicity. The semantics of Simplicity is in a way richer. It's more complete. It's a more complete picture. So we can embed these semantics into these semantics, which by a process which we call lifting. And the exciting thing we can do is we can take a Miniscript, we can take a Simplicity program, and we can check that they are equivalent in a way. Even though they are written in different languages, very different syntax, we can say, actually they implement the same check sig or something, the same key lock, or the same time lock, and many more complicated things too. So that's cool, and we are also working on that. Very briefly, I will talk about how we could integrate Simplicity into Bitcoin. This will be a very long process, of course. This is like 5-10 years into the future. But in general, we will integrate this into Taproot. So this will be a new Taproot leaf version, because as you know, Taproot has versions. It's meant to be extendable in the future. At some point, maybe Simplicity will have a tab leaf version number. I just picked any number. And you have the tab tree, which is used for the script path spend. And you have a lot of leaves. And many of them in this case have like the old, so they're standard Taproot leaves. And they have some Bitcoin script or some Bitcoin script that is actually Miniscript. But you could also have a new leaf, which has version C2 in this case. And this means it's a Simplicity leaf. And this means this binary, these bytes are actually a Simplicity program. So when we spend this, we use the Simplicity deserializer to deserialize, and we use a Simplicity runtime to run this. But this will coexist. Simplicity will coexist with Bitcoin script and Miniscript inside these tab trees. This is what we're targeting. And currently we're working on Liquid, so we have the Simplicity branch for Elements. We're working with the Elements team to integrate Simplicity into Liquid. Even though we know what we're doing, even though we put in the hours and make sure, and we actually prove many of the things we claim we know, there's theory and there's practice, so we must test these features on the sidechain, get some feedback, learn. We're currently working on the jets, try to see how long the jets take, and assign some weights. So this will be the next big step in Simplicity. To conclude, I talked about structured programs. The previous talk talked about structured programs. I talk about structured programs. So structured programs are good programs. Simplicity is a successor of Miniscript in many ways, in what it tries to achieve and in the way that it looks. It's a tree structure. It has all the benefits of structure, but it goes beyond that. So we have much more functionality. We can compute many more functions than that. We have verifiability, so we can prove. We can do what we might want to do, and we can also prove whatever we might want to prove. So let's hope this will lead to maximum adoption. It's up to you. It's certainly exciting. It's a very exciting proposal, and I hope that more people can get to know this in the future. And the next step is the Liquid integration. So I talk about the new blockchain language, so this is scary. Maybe to some of you this seemed like Pandora's box. It will destroy Bitcoin. And I hope I could convince you of the opposite. I hope I can convince you that even though it is powerful, first of all, we need this power, so Bitcoin needs to be future-proof, even though this will be a slow and very careful process. But at the same time, we can verify that our programs are correct, given that power. And we have consensus limits, so we do not have any DDoS. So this will not destroy Bitcoin, but it will help Bitcoin. So thank you.
Fantastic. Lovely talk. We have gone a little bit off script.